So just a quick reminder that your project proposals are due tomorrow by 4 o'clock. There's an assignment on TED to turn that in. If you're still struggling to figure out what your topic's going to be, where to find sources, remember that I have office hours today at 12 o'clock, so you can certainly come on in and ask questions about it then. Now the proposal is pretty simple. It's an abstract, so you're just going to describe kind of what your idea is, both the sort of science topic, but also the, if you're going to do a presentation or a creative part, particularly doing a creative part, kind of give an idea of what you have in mind for the creative part. Part of the purpose for that is just for me to make sure you're not trying to do something that's too hard. I usually don't have people who ask to do things too easy. It's mostly like asked to do something that's way too hard. So provide some description as far as you've conceived it so far of what you want to do for that. And then you should also have a list of your 2 primary sources. All right, if you have more, great. If you only got one, see if you can find another one between now and tomorrow. Now, a couple of you pointed out that I had posted some remnants of last year's project on there, and there was some reference to quantitative to be analyzed based on your quantitative question. That's not part of this year's project, so don't worry, you don't have to do a quantitative part to this project. It's really get into the research and sort of understand the research and delve into what the topic is, and then see if you can turn it into something that you can communicate either through a presentation or through something more creative. Okay. Those of you who may or missed the workshop yesterday on primary sources, I put those slides online in the project folder as well, so you can take a look at that. That includes the link to the Chicago style, so you can see the sort of bibliographic style that I'm looking for. Now, John brought up that one of the questions I said that, wow, I can't believe everyone got this wrong, was the one about, what's this one not working? Was the one about this one, resistance to bacteria, certain antibiotics, for an example of. And the answer is artificial selection. But John pointed out that last year the answer was natural selection. So those of you who answered natural selection actually looked at last year's midterm and actually did the right thing. So, so that was wrong. Artificial selection is right, but that's super confusing. So I just wiped that question off the exam. Basically, I just reduced the points that I divided your points by. So everyone's score went up a little bit. It's 2 points, so it's not that much. But thank you for pointing that out. I would have missed that. Okay. All right. Any questions? Yes, sir.
So, how come we're not part of the natural selection anymore? Like, it's not our intention to make them stronger. It's not like, are we part of the natural process? So when we do things unintentionally, don't we naturally select?
So evolution is not an intentional process. No, the Earth doesn't intend for giraffes to have long necks. We don't intend for giraffes to have long necks. The giraffes that have long necks survive. So by using antibiotics, we're creating an environment in which bacteria that are resistant to those antibiotics can survive over bacteria that are not resistant to those bacteria. So we've created an artificial environment in which that survival mechanism is possible. I'll give you another example. In the 19th century, when the Industrial Revolution started kicking up in the United Kingdom, there used to be kind of even number, actually, there used to be mostly white moths and a very few number of rare black moths. As the sort of 19th century progressed, early 20th century, there's so much soot and garbage on sort of walls and stuff like that. What you find is that the white moth population crashes and the black moth population becomes really popular because they can blend in with all the soot that's on the walls. So that we created an environment in which the process of evolution could take place. That process of evolution is still a natural cycle, as in, there's natural mutations. Some animals survive, some don't survive. But in this case, we are creating the environment in which that sort of survival mechanism takes place. So that's the difference between natural and artificial selection. Artificial is, we have done something to the environment, or we've set up some kind of conditions so that a certain type of animal is going to survive better than others. I mean, dogs are a great example. Cows are a great example. Like the cows that we have today for milking and for meat would never survive in the wild. I mean, they're like defenseless. So that's an artificial selection process. Right, but there, thank you for asking. Any other questions? Okay, so today we've got 3 presentations. We're going to start with Laura. Come on down. Oh, sorry, yes, one more question. Do we have any extra papers? I know we don't, so maybe if you have 3, kind of share one in half. You get 4. There you go. Yeah. All right, so Laura Castro is going to go first and talk about supergiants and life molecules.
My article name was Supergiants Do Life Molecules, and my topic was about this star named VY Canis Majoris, and it's in the constellation Canis Majoris, so that's why it's called VY Canis Majoris. And it's this very massive star that is 25 times bigger than the sun. And actually, if you place it in our solar system, it would reach Jupiter, I read. So it's very massive, and it is releasing a lot of energy, but so since it's a massive star, it's dying out pretty quickly. So in 1 million years, it will cease to exist. And since it's dying out so quickly, it's pushing out so much energy. And what they found at the University of Arizona, some astronomers found using sensitive radio telescopes, they found molecules and compounds that are necessary for life. So this is how it relates back into the class, because not only did they find oxygen and carbon thrown out by the massive energy, they also found sodium chloride, which is salt, phosphorus nitride, and molecules of hydrogen isocyanides. So what's important about phosphorus nitride is that phosphorus and nitrogen are 2 of the 5 necessary molecules for life. And phosphorus is actually found in adenosine triphosphate, which is the reason why living organisms have metabolism, and also like what we've learned is that it's found in our DNA. So given the right circumstances, if this star were to shoot out enough dust or the gas molecules, it could possibly collide with other gas molecules and then create another system. So yeah, it could create other solar systems, which could, with these molecules, potentially create life, like what happened here on Earth. Because on Earth, as we know, comets and meteorites have left dust on Earth that possibly helped also develop life here on Earth.
Okay, great, thank you, Laura. Any questions? Yes.
When you say that the sun is has 1 million years left to go,
Yeah.
does that mean it actually has 1 million years left, or does it have like 1 million years from the light we see?
From the light we see, I guess it's 1 million years left from where it is,
Okay.
not from where we see it.
Did the article say how far away?
Yeah, it said 5,000 light years.
Okay. So we're only seeing it 5,000 years in the past. So 1 million years plus 5,000 is a tiny little addition.
I was just gonna ask, are there any planets or any planetisms, I guess, around this sun?
Not from what I read. So they only found like molecules, and it's because it's like also very hot. So, and it, has a lot of radiation.
So there might be, we don't know.
Yeah, it's really far, and the tools that they used might be more sensitive, but I don't think they could detect planets around it.
Okay, any other questions? All right, so this detection, phosphorus nitride, is a pretty important one because it's very rare that we see any molecules with phosphorus in them. They just don't make the kind of transitions we normally see in the optical or infrared light that we look at. So radio is a good way of looking at these particular molecules, and so this is actually a pretty exciting discovery in terms of elements.
Yeah.
Okay, thank you, Laura. So please don't forget to give Laura some feedback on presentation and slide. All right, now we're going to listen to John Durkee talk about organic compounds in hydrothermal vents. I see a theme today.
Yeah, so for my presentation, I actually looked at 2 articles and kind of connected between the two. So the first one is this slide right here, and it talks about how organic compounds are made from basically dissolved carbon dioxide and the minerals inside of hydrothermal vents. So these vents, we suppose, can spontaneously create the organic compounds, very simple ones, the interaction between the carbon dioxide dissolved in the water, and it's called greigite, which is that iron 3 sulfur 4 in the vents up there.
Mhm.
Yeah. Okay. And the way it worked is the minerals inside and the structure of the greigite inside the actual hydrothermal vents acted like enzymes, or like, how do you say it? They resemble the way that enzymes work, so they initiated or helped initiate the reaction between these two elements or compounds. And this is essential because it shows that simple organic compounds can be made in nature without the presence of previous signs of life. And it shows how the simple molecules that we usually see, or the simple how it shows how the simple molecules that are necessary for larger carbon compounds are made. So essentially, this is what I said earlier, the surface and the crystal structures inside the vents act like a catalyst in the interactions between the dissolved carbon dioxide and the minerals in the vents. And this encouraged the chemical changes to occur, which led to organic molecules. And this small excerpt here really describes it well. So the surfaces behave much like the enzymes do in living organisms, breaking down the bonds between carbon and oxygen atoms. So this lets them combine with water to produce formic acid, acetic acid, methanol, and pyruvic acid. And once you have the simple carbon-based chemicals such as these, it opens the door to more complex life, carbon-based chemistry, and that leads to the next slide, which is the next article I looked at. And this took formamide, which is water and hydrogen cyanide, which obviously says up there, abundant on the early Earth. It's another simple organic compound. And it took that chemical, that compound, and they put it in an experiment where they shot it with high photon beams, which resemble the solar wind, and added asteroid dust with it too, just what's it called? To symbolize what like an asteroid to be coming on. And it produced things such as amino acids, carbolic acids, oxalic acids, sugars, and nucleosides. Nucleosides is important because it's the more advanced building blocks consisting of nucleobases linked to a sugar molecule. This is a good sign because those are rarely found in experiments and they're rarely produced. So it's a pretty good sign of how these can be formed from simple carbon chains, simple carbon molecules. And the connection of these two articles could show one possible way of life being created from non-living materials, from the simple carbon dioxide in the water and the structure of the hydrothermal vents to the eventual nucleosides and the essential signs of life and precursors of life that we like to see when we're talking about the forms of life. So yeah, any questions?
Okay, 2 questions.
It's not really a hypothesis, it's more of a way that could work.
So basically, did they like grind up a meteorite and set it up? So
Okay, so the way they did it, they took the meteorite dust, which I guess is the way they did it, and then they took that and they took the what's it called, formamide, and they took the proton beams and they put the formamide and the asteroid dust together and they shot it with the proton beams, and then they ran it with supercomputers as well. Yeah.
Another question? Yes, ma'am.
It's on the first slide. What kind of acid is pyruvic acid?
I can't answer that question. So, in terms of looking forward, this wouldn't be a good thing to put on my slide for the presentation.
Yeah, so we talked about this yesterday, that quoting things does not actually mean you're saying them. So if there are words that you don't quite understand, this is for you, but also for everyone. Make sure that when you're presenting your work, you know what those words mean. So it may be a good idea for the presentation you have anything like that to look it up. anybody know what peruvic acid is? Yeah. Yeah, please do. Yeah.
Oh, are these guys out in space?
Yeah, so actually, I think in March they found that Enceladus, I think it's the Saturn's moon, has hydrothermal vents, so that'd be a good place to look in terms of inside the solar system for early signs of life. So yeah, Enceladus.
Well, but this study, is this done on Earth or is this
Yeah, this
done-
is done on Earth.
This is done. Okay, so this is the stuff. This is done on Earth, but
Yeah, but the hydrothermal vents are also found on Enceladus. Just what?
Just that, me there.
That's the first one we found so far. Yeah.
Oh, that's what I presented in like on my news report.
connections. Okay, thank you, John. All right, so please provide John some feedback. All right, and video.
It's pretty hard to see, but that's a picture of Earth with red tints, and that's a picture of Earth with greenish tint. Later that makes sense. So everyone's trying to figure out the question, are we alone? And with the discovery of exoplanets, maybe in the thousands constantly, we're trying to figure out better and more efficient ways to find life outside the solar system. And so scientists and biologists, astronomers came together and created a database for microbial
As you can see your slide.
for like single cellular organisms, and they specifically like connected them with the color of the in the spectrum, and they used visible light and near infrared all the way to the short wavelengths of infrared, which is the 0.35 to 0.25 micrometers. And the way it works is because of the reflective properties, which are dominated by the absorption of light. So cellular light in water is reflected by the or in the infrared light. So just like Earth started off as a single-celled organisms, we're hypothesizing that other exoplanets could have single-cell organisms as well. So one way to figure that if they exist is to shine the infrared light and see what kind of tint pops up, just like Earth. If it's like a specific color, then they will associate that color to a specific microbial life. And currently, there's like 137 different organisms that they've collected from Earth, ranging from like habitable places from Earth and even extremophiles on Earth, which are pretty like harsh conditions to live in. And those are the ones that are like pretty new in the database. So they could possibly exist in exoplanets solar system. And okay, yeah, that was one more. Just as we can see like other planets, the hope is that other planets would be able to see us. And that's why they took pictures of Earth with different forms. And the pigmentation of organisms on Earth will hopefully be seen on other planets, proving the existence of other organisms outside of Earth.
Okay, we can leave it. Like 2 questions. Yes, 1, 2. Go ahead. Go ahead, put down.
Would that work? Like, would that process work on a planet that has, like, for example, ice on the surface, or like that would have life under the surface of the?
That was actually one of the topics of the obstacles in the way would be if a planet is covered in like an atmosphere that's can't shine light through, but they have like computer generations or they have these programs that clear the actual atmosphere so you can actually shine the light on the surface, which will reflect the light back and hopefully have certain pigmentation from the database.
Well, so I mean, those are computer simulations. So whether we could actually do that with other planets is probably another
Yeah.
question. But I think that's a good point. That if both the atmosphere could block out, we can't see the surface of Venus, for example, with our eyes.
And if it went through, it get caught in if there was too many.
Yeah, we have greenhouse gases, so yeah. And then if the life is underground, this won't help too much. So this is specifically to see if life on the surface.
Yeah.
Which we've had on Earth, so that's not unreasonable. Sebastian?
So you're saying that from space you can see the light, reflected, but like given off by like organisms, and you can tell what they are based on that light.
Yeah, there's on the spectrum, it's certain levels, like the micrometers, depending on which light is shown or given off, and which one is reflected. There's a specific number or pattern that shines the color, and that color is been organized in the database, so we should know which organism it is.
But from space, wouldn't organisms be too small for the light given off to have any significance?
The hope is that they're gonna large enough, there's a lot of those.
Like a big
Yeah, it's it's big enough so that you could actually see it. Because you won't be able to just see that one little cell.
Okay, for sure.
What's that?
Pollution.
Fog.
It's true.
That's light.
Green. Oh, okay.
So yeah, we can see light from space, at least in the one experiment that we can do right now. What's that?
When we went down the strips, the Lester was talking about it.
Yeah, remote sensing. So we can do remote sensing from an airplane and sort of map out what kind of vegetation there is based on the reflection of different colors. That was certainly something that was talked about, and that can be done from orbits of planets. The big question is, Minga, you're talking about planets that are in other places.
Yeah, it's outside the source.
Yeah. So how would we get that image?
You probably have to send some kind of space shuttle to never return and just remotely send images back to Earth.
Really long rocket ship. Yeah. Question.
I don't know if those are real pictures or are they artists?
No, they're straight from NASA.
Oh, okay.
They're artist renditions. Yeah. These are not real planets.
No,
This is
that's
the
Earth.
Earth.
That's
Yeah,
Earth, yeah.
but they're recolored.
Oh, okay.
Yeah. So it's a real planet, but
Alright.
in a different color.
Yeah.
I didn't recognize it.
Yeah, I mean, it's actually tilted a little bit.
Yeah,
So
like
here's
looking
the
at most
Middle East, Horn of Africa.
Oh, okay. Oh, that makes sense.
So you're biased to looking the Earth north up, but that's not necessarily the way it's supposed to be.
What's your name?
Amigdio,
Migdio.
How do you spell it?
EMIGDIO.
Thank you.
Okay, any other questions? Okay, thank you, Migdio. All right, so we're gonna be talking about some of this stuff today. This is always well timed. It's amazing. So we've talked about life. Oh yeah, if you can please, while you're thinking about it, just hand out your sheets now. So up to now, we've been focusing on Earth and life on Earth. We're going to start expanding our way out into the universe and starting with our sort of local neighborhood of the solar system and trying to understand how we might look for or identify, or at least identify the conditions in which life might thrive in the solar system today or in the past or in the future. So the first thing is going to sort of understand how the solar system got to be what it looks like, what is the patterns. What's the origin as far as we know about the solar system, and then we can start piecing that together and sort of seeing where are good places to live in this particular system. Now, we know there's one good place, and that is this place, our Earth, which we can see vegetation on. But it's a big question to ask: is this really the only world in our solar system with life? As far as we know today, it is. But we are just starting to get out and land landers and other places. I mean, we've been visiting Mars for something like 40 years. But as you'll see, many of the places that look like they're potentially habitable planets or moons are places that we actually haven't visited yet, or we've just recently visited. So it's still possible that we may find life even in our own solar system. So it's important to see what kind of conditions there are in our solar system, what's out there. Now, throughout this, I want to sort of make sure you have this context on sort of how these ideas of the solar system formation, how the planets form, sort of come into being, and sort of the whole scope of science. And so I didn't get a chance to do this earlier in the quarter, but the way kind of science progresses, particularly when you're doing some new environment or sort of looking at sort of new process, is you basically just start with observations and you look for patterns. And those patterns are called laws. And I know often it's like thought that the laws of physics or the laws of science are like the super amazing ideas of how everything works. But laws are just patterns, right? And they're specific patterns for what you're looking at. So there's Kepler's laws of planetary motion only describe the patterns of the motion of the planets in the solar system. That's it. Right? But they're patterns that repeat over and over again. And those patterns have been used to figure out things like how gravity works and how the solar system is formed and stuff like that. But the laws themselves are just patterns. There's nothing spectacular about them. Right? They're just patterns. Newton's laws of physics is just the patterns of motion. The law of gravity is just a pattern of how gravity works. Right? There's no understanding of necessarily how gravity is supposed to be doing that pattern, but it's a pattern that we can use to predict things. Yeah.
I don't know, just keep talking about gravity right now.
Yeah.
It reminded me of I think it was Mars, of having different types of gravitational pull around the surface.
Yeah.
Or around it. How can you have different levels of gravitational pull?
So it's very small variation. So what you can have is if you have, and we actually do this here on Earth as well. If you have, say, an area that has a lot of metal under the ground, then there's a lot more mass in that one little area compared to the area next to it. And if you have a very sensitive instrument that measures acceleration or gravitational acceleration, you can actually find buried heavy things based on the change in the gravity as you go across that surface. And so this is something we use on Earth to look for mines, for example. Like mining companies have extremely sensitive gravity meters, and they literally go around to find a place that's heavier, and that's probably a place that has some kind of buried metals. So yeah, but it's tiny variations. It's not like you walk over, you're like, oh my God. It's a little bit. All right, so we have these patterns in nature, and from that you sort of propose an idea of where that pattern comes from. So law is kind of actually the base of this whole process. The next part is the hypothesis. Why do we see this pattern? What's the cause of it? And then when you make this hypothesis idea and you test it experimentally, right? You make a new measurement, you make a prediction, you make a new measurement. Eventually, this sort of welds itself into a set of ideas that turns into a theory. So we have theories of evolution. We have theories of general relativity, right? These are really the sort of big concepts, the big ideas, how the universe works. This is asking the why of the universe. This is just the what, or how it works. These hypotheses are the why. So whenever you hear about the theory of something, that's actually far more important than the law of something. And the theory of something is something where it's really putting together ideas, trying to understand why this works. And then over time, once you have enough sort of theories built together that explains a very broad range of patterns, you have something that's called a paradigm. So paradigms are much bigger. These are, paradigms are like, physics is a paradigm. Like the idea that the universe is, follows these whole sets of laws and it can be quantified and explained. That's a sort of paradigm. Quantum mechanics didn't exist before the 20th century. It came in being. That's kind of the paradigm that we work in now, that that there's a sort of uncertainty in all of things at very, very small nature. So that's a paradigm of nature. It encompasses lots of different theories, lots of different ideas, but it's sort of a whole picture of how we think about the world. And all of these things are testable and can be overthrown. So we've actually had several paradigm shifts in the course of the last few hundred years of how we look at the universe, because some new idea came out with a new prediction and tested, and it was actually better. General relativity is a great example of that. Everyone thought Newtonian gravity was gravity, that's it. But Einstein showed through some experiments that, in fact, that's not the complete picture of gravity, but there's another whole sort of thing you have to think about. And that's why we have black holes and think about the beginning of the universe and all this other stuff. That comes from this new paradigm of how gravity works. So just keep in mind this structure as we talk about the solar system. So to start this off, we have to kind of look at where the patterns are in the solar system. So we've talked a little bit about a couple of them. All right, we talked about the fact that the sun is at the center of our solar system, and that it contains 99.9% of all of the mass in the solar system. So it's all concentrated at this one object, mostly made out of hydrogen and helium. That's a pattern, right? When we look at the planets in our solar system, we see patterns in them too. All right, we've got these sort of kind of two classes of planets, maybe three classes of planets if you divide these two up. You've got these kind of like large gas giants, the giant planets that are mostly atmosphere. Right? These are not solid surfaces; these are mostly gas bodies. In fact, we're not even sure Jupiter even has any solid like core inside of it at this point. Right? It's probably been evaporated away. And then in the inner part of the solar system, we have these little tiny rock bodies, mostly rocks and metals, right? Happens to be a good place to live on one of them. But we have these sort of different categories of planets. And another pattern is where these planets actually are in the solar system. All of those little worlds are in the inner part of the solar system, closer than about 3 or 4 astronomical units. Remember, that's the distance between the sun and the Earth, right? So they're all to the left of this or right, depending on where you're looking at this. And then these big planets are all on the outside. So that's an interesting pattern. Right? We can ask why would that pattern be there? It's a law that small planets on the inside, large planets on the outside of the solar system, because that's the pattern we see. Asking why is sort of where we have to come up with a hypothesis or theory. Yes.
In the last slide for Saturn,
Yeah.
I think the pole was like shining with blue.
Yeah.
Like is that also gas?
So this is actually the aurora around Saturn. So we talked very briefly about aurora with our Earth's magnetic field. And these are the charged particles from the sun that are coming in, getting trapped in the magnetic field, and then falling into our atmosphere. And the particles falling into the atmosphere, essentially heat up the atmosphere, and they heat up in different colors depending on what elements are in there. So Saturn also has a tremendously strong magnetic field, and the solar wind pulls in those particles and creates aurora on Saturn as well. We also have them on Jupiter. I don't know if we've seen them on Uranus and Neptune yet, but it's possible. I haven't actually looked at that. But yeah, anytime you see this kind of bright emission near the poles, it usually means there's a magnetic field around the planet. Which is another pattern. Okay. So these are the big things. Well, sun is the big thing. Then this is sort of the next hierarchy down. And then there's another hierarchy down below that where we've got tons and tons of these just little objects all over the place. And that includes asteroids that mostly reside between the orbit of Mars and Jupiter. That's another pattern. Right? Why aren't they just scattered everywhere in the solar system? Why are they concentrated in this one little place? And then we also have things that are kind of outside the orbit of the farthest planet, Neptune, which we call Kuiper belt objects. These are these sort of icy, rocky worlds like Pluto that are a lot more scattered, but they are, again, mostly concentrated outside of this place. They're not uniformly inside here. So there seems to be something that's separated out those two types of objects. And then even further out, we have comets, which come in from many, many thousands of astronomical units away and have these extremely steep orbits, elliptical orbits, and come in all different directions. So they're not sort of in this sort of circular disk structure. Yeah.
I don't know if this question's already been answered, but there's dark matter that keeps the galaxies like flattened together.
Mm-hmm.
Is it possible to have dark matter within and having that's why solar systems have those? Like for example, between Jupiter and Neptune, I guess it would be dark matter that's keeping the asteroids separated.
So we'll talk about the flattening of the galaxy just a little bit because that's one of the patterns we're going to talk about. Dark matter doesn't necessarily keep the galaxy flat. That actually turns out to be just the way that it rotates. But it does keep it together. And it keeps it together because when we measure how fast the stars are going on around the galaxy, they're going around much too fast compared to the visible mass that we see in the galaxy. So that's really the reason we call it dark matter, is that there needs to be more mass to keep those stars from not flying off. And you can't see it. So dark matter. In our solar system, when we look at the orbits of the planets, of the asteroids, and Kuiper belt objects, there doesn't seem to be any missing matter. So there probably is some dark matter. I mean, there's probably dark matter floating around in this room right now, but it's a tiny, tiny fraction of the local matter. It's only when you get out to the whole scale of the galaxy and you get this sort of like low density amount of dark matter that starts to add up, and it adds up to be a lot of stuff. But it turns out here in the solar system, we actually have a lot of stuff packed into the solar system, even though there's huge distances between things. So the matter density is higher than the dark matter density. We can't even measure the dark matter density here. I would say I should be careful of that. We could measure the dark matter density. People are trying to do that. But it's not as obvious as when we look at galaxies. When we see stars going around galaxies. So there probably is dark matter, but we can't measure it, not at this scale. Okay. All right, so we've got these different hierarchies of places and different patterns. Just to focus again on the Kuiper Belt objects, I should point out that we're going to have our first visit to one of those Kuiper Belt objects just coming up in a couple months. This is the New Horizons spacecraft. It's going to be passing by Pluto on July 14th. So we can have a whole debate about whether Pluto is a planet or not, but this is the first and probably potentially the only time we actually send a spacecraft to visit this distant icy ball rocky world. So it's very exciting, and we've already starting to get some really interesting images just as it's coming in. This is an animation that was released a couple weeks ago. Turn this off, you can see this. Pluto has 4 moons. Its biggest moon is Charon, and it's this little dot that's going around Pluto here. And what you see in sort of this kind of like change in brightness and darkness is Pluto actually rotating around its axis. So, and this is a zoom in of that. And what it looks like is that it's not circular, or maybe it's circular, but it's got like dark and light patches on it. This is an interesting pattern, and we don't know why it is, but in the next few months, we're going to probably get close enough to Pluto to actually make a map and see exactly why it's light and dark like that. Sebastian, yeah.
Could that be from like the sun, like the weight reflected off of it, or is it like the sun straight like behind the camera here?
So I'm not sure if the sun is directly like the projector, the sun's projecting directly this way. But during the course of its approach, the sun angle is not changing, right? So even if it's up off an angle, it's going to stay at an angle. So if it was a perfectly smooth, perfectly uniform body, then it wouldn't change brightness like this.
Okay.
So again, this either means physical structure or some kind of coloration or shading on the surface, which could mean lots of things. Different materials, how those materials get distributed around. These are all questions that people are going to be able to answer in the next 2 months.
This is the closest we've seen it so far.
Yeah. Yeah, we're only 100 million kilometers. Yeah, I mean, it's like next door, you know? And this was about, like I said, this is April 17, 12, 15, 14. This is over the course of several days. This is not the real time of Charon going around. Yeah. But, we're now another 2 or 3 weeks on, so we're going to be much closer. I expect probably in the next month you're going to see a lot of stuff on Pluto. And Melissa.
When did they launch?
Oh, they launched, I think, 2006. Kurt, do you remember?
I don't know.
Okay. Well, you say, whoa, I mean, that wasn't that long ago. It got all the way to the outside of the solar system. Yeah, it takes a long time to get these kind of spacecraft out into the outer solar
What blows
system.
my mind is like, scientists have to calculate the intercept course.
Yeah,
Years ahead, like decades ahead.
yeah. It's crazy. It's super great. I mean, yeah, this is a tiny little world, and it's amazing.
Your
I totally agree.
calculus is off by like a tiny bit.
And the thing to keep, it's also amazing that in order to get the spacecraft out here, so it's not like this thing has like a huge rocket that's just been pushing it the whole time. The only way we were able to get any spacecraft out in the outer solar system is we have the spacecraft pass by planets, and essentially it picks up some of the momentum of the planet. It slingshots around. So it has slingshotted around Venus and Earth and Jupiter to get to Pluto. So it had 3 close encounters with planets, and it still ended up in the right place, which is crazy.
It's like playing pool with planets.
Yeah, it's amazing. Was there another question? Yeah.
Well, it's not really like regarding with Pluto.
Yeah.
But, I was just thinking, like, what if, like, in terms of Earth, if there's no gravity, we'll be just like floating around, right?
Yes.
But if there's no like force between like sun and each planet, would it like fall or just like floating around in space?
Well, I wish I don't have a demo to do this, but you probably maybe seen like, if you like swirl like a rock on a string or something like that, and you let go of the string, what happens to the rock?
Just
Yeah, but it goes in a straight line,
Yeah.
right? So wherever you let it go, it just goes in a straight line. That's Newton's laws of motion. So unless there's a force acting on something, things move in straight lines. The only reason you have something moving in a circle is you've got a force that's pulling it inward. So, if gravity turned off for some reason, then the planets would just go off in straight lines.
But you wouldn't fall like vertically, right?
Like here on Earth?
Yeah.
Or would you fall vertically into the sun? Is that what you're saying?
No. That's like because there is no like limit to the universe yet, right? Because it's like still expanding, and itself. My question is like,
Yeah.
if there's no force between Earth and the sun,
Mhm.
then would the Earth just like fall like this way, or just go this way?
No, it would just go in a straight line.
Just straight line.
Yeah.
Okay.
So we're moving about 30,000 meters per second right now. I don't know if you can feel it. It's fast. There's no wind blowing my hair, so it's hard to tell, right? But if the sun gravity somehow turned off in some way, then we would just go in a straight line at 30,000 meters per second.
Okay.
And until we just keep going, right? Until we ran into something.
Okay.
Other questions? Yes.
So we don't know if Pluto is circular, and we've never seen it.
So the images that we can take from here on Earth aren't sharp enough to resolve the planet. So, Jupiter and Saturn, these are big planets. And so, we can get a big enough telescope, like the Keck telescopes, for example, we can resolve those planets. Pluto's too far away. So, and it's, like I said, it may be that it's circular, but it's just colored, but we can't tell that right now just from these like little pixels on here. We need to get closer to both see the actual coloration of the planet before we can tell whether it's circular or not. But yeah, we don't know. I mean, it should be circular from everything we know about how planets form, but we've been fooled before, as we'll see.
How good is this like camera quality? Because I mean, technology is advancing very fast, and will they send out another one just so this spacecraft?
Well, no, like I said, this will be the last one because this is these are expensive missions.
We did not have Blu-ray back in 2006.
Well, it's even worse than that because when you send things out in space, you have to have a very proven safe technology that you've tested in the kind of environments that we're putting this out in. I mean, space is not like a nice, cozy place. Right? There's cosmic radiation coming in, and it's freezing cold, and so the equipment that's usually on these spacecraft is typically 10 or 20 years older than when the spacecraft left. So this is probably 1990 technology cameras. I mean, we have way better cameras on our phones probably than what's on the spacecraft. It's just that it's on the spacecraft, not on your phone. So it's still better that way. Yeah. So I mean, there's all these stories like space shuttle. I used to work on a project where we had a camera on the space shuttle, and we actually had to give the astronauts a ThinkPad laptop because there were no computers on the space shuttle because it was built in 1970s technology, and there were no PCs then. So.
Are they trying to fix that with like laser printers now, like 3D printers? Like trying to build so that they can take less material up there and then just build itself.
Well, I mean, laser printers are a manufacturing technique, but you still have to test the materials. So even if today there's a project on campus actually, they're trying to laser print spacecraft or like a little spacecraft for a project.
If I do like a rocket engine or something?
Yeah, there's people that talk about laser printing rocket engines, but like you have to test those for like 5 or 10 years before it goes up. So there's always a delay. I mean, you'd be amazed at how low technology there is to get into space. Okay. All right, so this is the outer solar system. We can also look at how these planets are orbiting. So this is actually to scale. I mean, the planets are not to scale because you wouldn't see them in the scale. But this is to scale in terms of the speeds and the directions. And there's a couple of things to notice. One is that The things in the middle are moving pretty fast. This is, of course, not in real time. But things in the middle are moving really fast. Things on the outside are moving very slow. This is Kepler's laws, right? The further you away from the sun, the slower you're moving, right? But what's also unusual about this is all the planets are going in the same direction. That doesn't have to be the case, right? Gravity doesn't care which way you go. And Kepler's laws don't care which way you go. But for some reason, all the planets are moving around in the same direction in their orbits. Yes, Vincent?
Isn't there like one planet that's going the other way?
Well, so there's rotations. We'll talk about rotations.
Oh.
But in terms of the orbits of the planets, they're all going around the same direction. And not only that, these are the orbital planes. Let me get here. These are the orbital planes of the planets. What do you notice? They're all basically the same, within a couple degrees of each other. They're all orbiting, except Pluto, which is an oddball, right? An oddball for many reasons. But all these other planets, all the inner planets, all the gas giant planets are all in the same plane, and they're all going in the same direction. Right? That got to be an important pattern. Because that, again, gravity doesn't care if you're tilted one way or the other, right? Doesn't matter which way you go, counterclockwise or clockwise. That must be a pattern of how this system got into place. Right? A pretty important one. And I'll just say one last thing is that the orbits are actually also very circular, right? If we go back to this plot, you can have, again, in gravity, you can have extremely eccentric orbits. You can have comets that come in here and come right back out. But all the planets have almost exactly zero eccentricity. Right? They're almost perfectly circular orbits. Again, a very interesting pattern. All right, so, and then last thing I was mentioning, you mentioned rotation. So most of the planets, not only are they orbiting around the sun in this counterclockwise direction, this is if you're looking from the North Pole of the Earth, like flying above the North Pole, look down the solar system, maybe going this way. The sun rotates counterclockwise, and most of the planets rotate around counterclockwise. It's like there's a preferred direction for our solar system. Now, not all of them. So you're right, Melissa, that some of the planets are orbiting in weird ways. Venus seems to be very slowly rotating the other direction. It's still orbiting the right direction, it's rotating the other direction. And Uranus is tipped all the way over outside. It's like a little wheel going around the solar system. But those are the only two exceptions. All the other planets seem to be rotating in the same direction in which they're orbiting, which is the same direction that the sun is rotating. Everything seems to have some very strongly preferred direction, with some exceptions. Yeah.
Is it possible that Venus is orbiting the opposite direction because it got hit?
Well, so if you're rotating and orbiting are different things. So it's orbiting in the same direction. Its rotation, maybe going. So that's one possibility, is that perhaps it got hit by something and knocked in the wrong direction. It might have been tipped over in some way. Spinning planets are like spinning tops, and there are some tops where you spin them, they flip over upside down. That's a possibility. Okay. And then actually one last pattern is around the giant planets and even around Earth, the large moons are also going in the same direction, with a couple of small exceptions. Neptune's moon Triton is going the opposite direction. We'll explain why that might be in a little bit. Again, there seems to be this preferred direction, this preferred rotational direction in our solar system. So here's all these patterns I talked about. Most of the mass is in the sun. We've got this difference between inner planets, outer planets, and kind of these distant, icy little rocky things. All the planets orbit in the same plane. We call that the ecliptic plane, and in the same direction. Most of them rotate in the same direction. Most of the moons orbit in the same direction. And then we have these comets that have kind of weird orbits that really don't follow any of these patterns. It seems to be something else. So these are the patterns of the solar system. So how do we interpret this? So, I mean, these kind of patterns were known back in the 17th century when Kepler was devising Kepler's laws. Right? He was measuring the rates, but he could also make these measurements about where the planets were, which direction they're orbiting, etc. So there's sort of two classes of theories that came about to sort of explain this, how these planets came to be and why they have all these patterns. One of these is called the catastrophic hypothesis, and basically the idea is that the sun was just a nice normal little star until something came by and kind of ripped some material off. And as it ripped that material off, of course, it ripped it in a certain direction, and that would sort of pull the material around into some kind of circular motion. That's sort of the idea. Right? Now, that's a challenge because if that's true, stars in the galaxy are really far apart from each other. what's the distance between our star and your star? 4 light years. Okay, that's that time scale light years, the distance scale light years, right? That's much bigger than our solar system and much bigger than our star, right? Many orders of magnitude bigger. So the chances of stars passing by this close is extremely rare. I think I know of one example, and that was actually already a binary system, so it wasn't something that was going to pass by each other. So for this to be true, our solar system would be extremely rare, right? We wouldn't really expect to find many other planetary systems because this would be a very rare possibility. Now, back in the 17th century, who knew, right? That's a perfectly valid possibility. Now, of course, we know there are many exoplanets out, many planetary systems out there. So this doesn't seem to be the case because it couldn't be this rare of an event. The other idea, which came from Laplace back in the 18th century, was more of a sort of development process, that the process of the sun existing or being in sort of evolving early on would have naturally given rise to a planetary system. And his idea was a little bit different than what we think about today. His idea is that you have this rotating star and it wants to slow down, right? Maybe it's rotating too fast. And it does that by just kind of pushing material away from it along this equatorial region. And that carries away angular momentum, right? The spinning momentum of objects. And that angular momentum carried away would then, these disks, these rings of material would then eventually collapse into planets just through gravity. The strength of this idea, at least in terms of an evolutionary idea, is that this could happen around any star. And so it predicts that there might be many planets out in the galaxy. And of course, that's what we see today, right? Not that he would have known back then, but that's certainly what we see today. So these kind of different classes of ideas, catastrophe or evolution, give rise to very specifically different predictions. And so we can go out and make observations to determine which is correct, right? Now, I have to make sure I'm clear. This is not how we think the solar system formed, but at least this is the class of way that we think the solar system formed. How we think the solar system formed is similar, but a little bit different. This is called the solar nebula hypothesis. And this is really the best idea that we have on how our solar system, and in fact all the solar systems in the galaxy form. So sort of the idea, again, idea is a hypothesis, is that you start off with a really large cloud of very low density material. All right, that's the kind of stuff that we see, for example, when we look out and look at the galaxy, galactic plane. We see all of these sort of dark patches all across the galactic plane. These are massive clouds of gas and dust. And the idea is that those clouds of gas and dust, through gravity, attractive force, collapse in on themselves. Now, those big clouds have just a little bit of spin, right? They're in a galaxy that's spinning around, so they're going to have just a little bit of spin, even though they're so big. And in the process of collapsing down, that spin starts to spin up fast, just like an ice skater bringing her arms in. That little cloud that's just barely rotating will start to rotate really fast. And the material that's in the sort of plane of this rotation is going to have a harder time making it to the middle than the stuff that's on the ends. And so you very naturally, with this idea, end up with something that looks like a pancake, right? Some kind of this structure, just through angular momentum conservation. And then the idea is that out of that disk is where the planets form. So there's a bunch of predictions from this. One, there should be large clouds of gas and dust in the galaxy that form stars, and we know that's true. We should see the disks of gas and dust that form from this collapse process around very young stars that haven't formed their planets yet. And then we should eventually start to find planets in those disks as they collapse out. And the remarkable thing is that it's really been in the last 5 to 10 years where we can actually say for sure that those predictions have borne out. So these are pictures of stars. I believe these are in the Orion Nebula. The Orion Nebula, you can see it. It's in the Orion constellation. It's kind of right near the sword. We actually looked at it during our night lab. And these are young stars, about 1 million years old. And the pictures you're looking at, you see these kind of lines going across the middle here. These are dust rings that we're looking edge on, and they're actually blocking the light of the star. And the light that we see out here is just reflection off the sort of flared ends of these disks. So these are the disks that model predicts. And we see these things all over the place, particularly around young stars. We see them both edge on like this, and we also see them face on, where we can actually see the sort of circular structure of the disk. So that is, observational proof that that idea is right. And then again, just in the last sort of few years, we've been able to make that connection between the disks and the planets themselves. So this is a system, I don't know if you've ever shown this picture before, but this is the Beta Pictoris system. It's again a nearby young star. It's about 10 million years old, 5 to 10 million years old. So there's kind of a merge of two different images. The star is right here, but it's been blocked out, so you can block out the really bright light that would otherwise just completely swamp the image. When you do that, you can see this sort of line of material. That's hot gas and dust that's emitting in infrared. That's the wavelength that hot gas and dust will emit. And it's, again, a disk that we're seeing edge on. And just recently, in the last few years, we've been able to tamp down the light from the star so much that we actually now can see this little bright thing next to it. And this is a planet. This is a big planet, a giant planet that's right next to the star. And we've actually seen it kind of pop out on both sides, and it's in line with this disk that we also see. So this image makes a direct connection between this idea of a disk forming, which we know are all over the place, and that planets form in those disks. So again, an example of the scientific process, you make a prediction, you go out and you see if you can actually test that prediction with observations in this case. And indeed, you can see this is happening. Here's another example, just because these are all very exciting, very new. This is, I've probably shown this image before, this is the HR8799 system, which has 4 planets, 4 little dots going around this star that's been, again, blocked out, so it's not so bright. And it's been observed over several years, and these things are all moving, and just like our solar system, moving in the same direction. And they're following an equivalent of Kepler's laws with a different mass star in the middle. And I shall say, this star also has a big gas disk around it as well that's kind of outside this picture. So it again makes a connection between disk and planets, and the same idea that they're all rotating in the same direction. So this is all stuff that's, and this image is from 2008, so this is all stuff done in the last 10 years. They actually have this picture. Yeah. Yeah, so that's the idea that, and we'll talk about it in just a little bit, but you spend about 1 million to 10 million years making planets, and those planets will sort of gobble up a lot of that mass. So we'll see that in just a second. And eventually you get to the point where you have our solar system where you don't have a lot of gas, but we still do have gas and dust in this ecliptic plane. And you can see this if you go to a really dark spot right at sunset. You can actually see sunlight reflected off this disk of material in our own solar system. And it's at a different angle than the galaxy because our solar system isn't aligned with the galaxy. That's how you know that's our ecliptic plane. So you actually can see it from a really dark spot. So it's still there, but it's very, 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 very low, very much less than they see in these systems. Okay, so let's see here. So this process of collapse is also important in understanding why the sun is the way it is as well. This very massive central part, 99.9% of the solar system, which is fusing hydrogen. And that has to do with energy, right? Gravity is a force, and all forces have an equivalent energy. So for gravity, that's potential energy, gravitational potential energy. When this cloud starts off really big, it has lots of potential to collapse, right? When it collapses, that potential energy has to be converted into some other form of energy. And depending on the sort of steps of the process, ultimately that energy ends up as thermal energy in the sun. So a cold gas, huge, parsecs across, many layers across, can end up to be the size of the sun, and the process has to release a lot of that potential energy into heat. And that's why the sun is an object that can, and actually all stars are objects that can fuse hydrogen. You need a lot of heat to have those fusion reactions happen. Where does that heat come from? It comes from the collapse. So this picture not only provides an idea of how the planets got into being and why they have these patterns, but also why stars do what they do, why they fuse, how they're able to get hot enough to fuse. It's that gravitational collapse that provides the kind of kickstart energy to get hot enough to start fusion reactions. Okay. So now we have another pattern we need to talk about, and that's these types of planets, right? So we know that planets can form these disks, but why do we have these sort of differences of planets, terrestrial planets on the inside, gas planets on the outside? And part of that is going back and looking at what the conditions were inside of this disk when the sun was very young. And one of the most important things is what is the temperature of the disk. Right? It turns out that temperature depends, fairly and exclusively on how close the material is to the sun. So one of the properties of light that we talked about early in the quarter is that as you move away from a light source like the sun, the brightness drops off as the distance squared. And that's because the light coming from the sun has to fill these spheres. As you get further away, those spheres get bigger and bigger. They get bigger as distance squared. That's how you measure the surface area of a sphere. And so the energy flux, which is the energy per area per time, for example, goes down as 1 over distance squared. So the further away from the star, the less light you get. That light is energy, and that light energy absorbed by material turns into what kind of energy? Yeah, exactly. So this, part of that midterm exam question, right? You've got light, you absorb it onto material, that becomes heat. So we can also predict, based on how far away something is, what the temperature of that surface or that material is going to be. And it turns out the temperature goes off as 1 over distance to the 1/2 power, right, square root. Right? That has to do with the sort of sigma t to the 4th for black body radiation. But these are just patterns that we just know from basic radiation, properties and interaction with matter. So that temperature going as to 1/2 power. So if we were to plot the temperature of our disk, our early disk around the sun, as a function of distance in astronomical units, this is the temperature that you would get inside that disk. And notice that it starts really hot, right? That's because the surface of the sun is really hot, right? 6,000 Kelvin at the surface. So if we were at the right surface, it would be 6,000 Kelvin. But as you go further away, it gets colder pretty fast. What's labeled here are all the kind of things that you can have as solid material at these given temperatures. These are the melting or boiling points of these different types of materials. So, the hardest thing to melt, so you need these, industrial sort of kilns, is metals, right? Molten iron. Right? This is one of the last things that was developed in technology for, sort of early humans. And so that requires the highest temperatures. So you're only going to see evaporated or molten iron if you go really close to the sun. Past it, it's all solids, right? It's all rocks. Silicates and rocks, right? Those are also hard to melt, but not as hard as melted metals, so they can be solid at cooler temperatures. You have to get down to 0 degrees Celsius before you get water ice, and then you can also get other kinds of ices as you go past that. Right? These are the solid objects, the solid materials that were present in the protoplanet disk. You got closer than this, water wasn't in ice form, wasn't a solid form. It was a gas or a liquid, most likely a gas. But if you're here or beyond, water is cold enough to be ice, a solid. Now, the reason that's important is that solids are the things that build planets, right? You can't build a planet out of just some gas. It just doesn't stick together well enough. Right? It dissipates. You push some gas together, it presses itself out for pressure, right? It slips out in some other direction. You need to have things stick together that are actually solids, yeah.
Then how are Jupiter and Saturn?
We'll get to that. Excellent. Good anticipation. Right. So to start building planets, let's put it that way, you need to have solid material. To start building anything, you need solid material. And where these solid materials exist is actually what gives rise to what kind of planets. And so in particular, where this water ice line is, where water ice is allowed to be solid, we call that the frost line. Frost is a solid form of water. Within this frost line, which is again about 3 to 4 astronomical units, which you should remember because that's the dividing line between the terrestrial planets and the gas giant planets. At 3 to 4 AU, if you're inside that, you don't have water ice. It's a gas. Outside of that, you can have water ice in the solid. So the place where the terrestrial planets formed, there would have been no water ice to actually build those planets. Whereas outside that, there's plenty of water ice. In fact, there's really plenty of water ice because ices are way more common in our universe than metals. I've shown this before. This is just the abundance of different elements versus their atomic number. And this is sort of a universal abundance, and this is on a log scale. So this is a huge range. Most common element is hydrogen. But ices like water, ammonia ice are made of things like carbon, oxygen, and nitrogen, which is not labeled for some reason. Those are fairly common in the universe, right? And obviously hydrogen is very common, so H2O it should be all over the place. In fact, we do see it all over the place. Whereas in order to get down to iron, magnesium, silicon, the things that we see that are in rocks, you actually have to go down by an order of magnitude in abundance. So there really should be 10 times less of this rocky stuff around, or metal stuff around, than the icy stuff, no matter what phase it's in. And that's a key point, because the more solid material you have, so you need solids to make planets, but the more of the solids you have, the bigger the planets you can make. And that's exactly what happened in our early solar system. So actually, let me go back a slide here. So inside this frost line, your building blocks are only metals and rocks, and you don't have a lot of them. So what do you end up with? Small planets, like the Earth, like Mars. Out here, you've got ices, and there's 10 times more material in ice than rocks and metal. So what do you end up with? Big, fat planets. Right? Now, you mentioned gas, right? So I haven't talked about hydrogen, because hydrogen doesn't form a solid until extremely low temperatures, right? Much too cold to be in here. But if you make a big enough rocky, icy kind of combination planet, it turns out that you can actually then start to suck up all of that gas just through gravity. So the hydrogen and helium that was just floating around through our disk, because it's just there in the universe, was attracted to our proto-Jupiter and proto-Saturn and proto-Uranus and proto-Neptune planets. And that's what built up their atmospheres. So essentially, they kind of made their own mini solar system. Our sun attracted lots of gas because of gravity. Jupiter and Saturn also attracted lots of gas because of gravity. And they made their own little planetary systems as well. That's what we call the moon systems around Jupiter and Saturn. It's essentially like another little solar system within our own solar system. But it's made possible because they can make really massive planets because of all the ices that are out there. All right, so the kind of picture that emerges from all this sort of story of building is that you start with some disk of material, right? It's, you start with a big cloud, it collapses down, makes a little disk of material. Out of that disk, you start to just stick things together into solids. Molecules and atoms start to make solids. That's called condensation. There's like condensation of raindrops in our clouds. Once they start to make bigger bodies and sort of make things like rocks and asteroids and stuff like that, that's called accretion. And then you have sort of a split depending on where you are. If you're inside the frost line, where you only have rocks and metals as solids, you end up making kind of small things. Right? No bigger than, we estimate, about 15 times the mass of the Earth. Now the Earth is the biggest one in our solar system, but as we'll see, there are actually even bigger earthy things out in other solar systems. If you're outside the frost line, you can make much bigger planets because of all that ice, and then they start to attract the gas, the hydrogen and helium, and then you end up with these big gas giant planets. So this is the theory. Right? This is not a law. It's not something we observe. This is something that happened in the past. This is the idea that we have for how our solar system came into existence. And up until the sort of 1990s, when we didn't have any other evidence of other solar systems, this is kind of how we believe all solar systems were made. When we talk about exoplanets, there's going to be some changes that are on this hypothesis because of what we've learned from other solar systems. But all of this sort of matches the patterns that we see in our solar system. And they provide sort of a nice logical flow of how things work. So that's kind of the process of the science. All right, so just to wrap up, I want to show just a couple more quick little things that are interesting about our solar system. So there was mention about like what happened to all the gas and dust. So not long after these planets form, a lot of the rest of the stuff gets cleared out just from gravitational interactions. Right? So in particular, the gas gets accreted onto Jupiter's and Jupiter, Saturn, so that goes away. Many of the little bodies that were trying to form planets get scattered out, and that scattering, particularly out to the outer parts of the solar system, is the origin of our comets. And the fact that those comets are mostly made of ice means they formed outside of the frost line. So those were building blocks for the big planets that just got scattered out before they could stick stuck onto a planet. So this got scattered in all different directions. We have this other thing I talked about with the asteroid belt, where these are actually rocky metal objects, right? They're inside the frost line, but they're still little bodies. And we think that you've probably heard the idea that maybe there was a planet that got smashed. In fact, what we think is that it was just there's too much gravity from Jupiter here, too much disturbance from Jupiter stirring up that area that things just couldn't stick together and make big planets. So you just end up with lots of little worlds, the asteroids. Right? But importantly, made mostly of rock and metal, because that's where they were forming in the first place. Right? Composition gives an idea of where they formed. Now, an interesting thing about, so that's the idea of how their composition is, and we can tell that from the radius and masses of some of these asteroids. But they're not all rock and metal, and some of you may have seen this news story about the asteroid Ceres. Ceres has got a great history because it was discovered back in 1800, and at that point was believed to be another planet. This is before Neptune was discovered, for example, so I think at the time it would have been the 9th planet. And soon they found lots of other asteroids out there that were just as big, and so they relabeled this as an asteroid. We have another spacecraft that's out by Ceres right now called the Dawn spacecraft. This is a really fascinating spacecraft because it moves by ion propulsion, so it goes really slowly, acceleration, but it does that continuously and eventually goes so fast and you can see it basically anywhere. So this doesn't require these sort of planetary sort of encounters. It can actually direct itself almost seemingly, but it has to do it really, really slowly. So this is not something we do for example, human spacecraft. So it's come into to Ceres. It came in around the beginning of this year, and it took this image of this crater here with these really, really bright spots of light reflected back. And there's been so much speculation about what that actually is. So many of the astronomers think that in fact this is water ice that's just below the surface of Ceres, and because it's at the bottom of a crater, it's sort of exposed. That would be extremely exciting because one of the questions about Earth is where does all the water come from? Comets are kind of too far away, and they also have a different sort of composition than the water that we see here on Earth. Asteroids have the right composition of water, but we mostly thought that they've been too dry. If that's really subsurface ice, that means there's actually a lot of ice on Ceres, and maybe it's the asteroids that deliver a lot of water. Now that's one possibility. A lot of people think that this is probably alien civilizations, landing lights for getting into the sort of terrestrial little moon here. I don't know. It could be. Who knows? So we'll find out more about this in the next couple months. And as I mentioned, we think that this is one way of delivering water. When asteroids come into the Earth, we call them bolides. These are, asteroids that blow up on the surface of the Earth. This is kind of a map where all the bolides have happened in sort of the last 10 years. And by energy. And I want to raise attention to this big spot. So the size of the spots is the sort of energy contained in the bolide. And this one happened in 2013. And you might remember this one. I don't know if I have sound here. Oh. Actually, I don't think there is sound. This happened a couple years ago, and all the sort of footage you're seeing is the asteroid not crashing into the Earth, but in fact, just as it blows up in the atmosphere, it creates a sonic boom. And this is the sonic boom traveling down to the surface and blowing windows out and stuff like that.
So it didn't hit the Earth?
So there is a little bit of fragment that's been found in some ice lake. There's this perfectly round hole in one of the ice lakes, but it's tiny. And the fragments that have been found so far have been very small. What must have actually created the burst, the sort of explosion, had to be much bigger, about 20 meters across, which is big, right? But big, and it completely blew up. And so all we really have is little fragments. And that's typically actually what happens with asteroids, is they blow up. But one of the reasons they blow up is because they're not made of pure rock and metal. If it was a pure cannonball, it wouldn't have blown up. It would have just landed and just destroyed stuff all over the place. But this is, again, evidence that asteroids have a lot of water in them, because if they're heated, it's the water that evaporates first, and all that gas basically blows the asteroid up. So we have a lot of evidence now to suggest that asteroids are not just rock and metal like the inner planets, but may have a significant amount of water. And if that's true, that might be why we have water here on Earth. That's one of the possibilities. Okay, that's it. I'll see you guys next Tuesday. Don't forget to turn in your project proposals tomorrow, and don't forget your homework due next Monday. Okay. And I have office hours if you want any questions about your project proposals.